This is our proposed exercise. We have a system with a vertical elastic support, a fixed support, and a moment applied in a point. All of the bars are made from the same material and have the same section, giving us all this data. There is a thermal load applied in bar BC, which has these characteristics. Our goal is to compute the diagrams of the system and then attain the vertical displacement in point A. First, we compute the degree of indeterminacy of the system. We have 4 reactions, as explained here, and per usual we have only 3 equations. This leaves a degree of indeterminacy of 1. That would mean that we cannot solve the system through the usual procedure. In order to be able to compute these things, we substitute this vertical elastic support with a load of value x1 times newtons. Then with this compatibility equation, we can know that minus the displacement in 1, 0 divided by the displacement in 1, 1 will give us the value of this force. When we have that value, we can solve this system. So we first set up our system 0, which is a system only with the external loads, in this case only this moment. We set up our 3 equations: all vertical forces equal to 0, all horizontal forces equal to 0, and all moments at certain point, in this case C, equal to 0. This is very simple and gives us the reactions. With the reactions, we can compute all of the diagrams. The axial and shear diagrams are very simple as they are null. They have no value other than 0. The bending moment diagram is very simple as well, giving us only these 2 values. System 1 is equally simple. We only have to put a load of 1 in place of x1. We set up the same system of equations, we get the reactions, and we attain the diagrams. Once we have the diagrams for both systems, we can use them to attain the displacement in 0, 1, 0 and in 1, 1, using the tables provided to us to solve these intervals. In this computation, we only take into consideration the thermal load and not the effect of the elastic support. The effect of the thermal load is based on K0, which is equal to twice the average temperature, which in this case is 50 degrees, times alpha divided by h, which is 0.1 meters. For this other computation, we don't have to take into consideration case 0. Instead, we take into consideration the effect of the elastic support. The displacement is equal to the force divided by the constant of the support per Hooke's equation. These 2 data give us x1. Now, with x1, we could go back here, substitute x1 and compute the system from scratch. Instead of that, we can simply use these 3 equations to get the diagrams. It's very simple, no point in going in depth into this. In the same vein, we could use the usual procedure to solve displacement in point A for this system once we've computed x1. But since we are being affected by a vertical elastic support, we can use Hooke's law. And that law gives us that the displacement is equal to minus the force divided by the elastic support constant. This gives us the displacement, the vertical displacement in point E, and thus solves all of the goals that we had for this exercise.